Okay, so today we have our very own Marco. Marco got his PhD from Technical. He was then researcher at LIP and then as a fellow. Within ESA, he started a new project that's innovative and well received by the community, which is called CONRAD, and it's the topic that we'll hear about today. For a few months now, he's been back at LIP, where he wants to, among other things, continue developing this new project. Besides that, he's also has leading responsibilities in different space missions, and he's the team leader for the radiation detectors in both JUICE and the Bepi Colombo mission. So let's hear it from Marco.
Thanks, Cristóvão. So hi everyone. Like Cristóvão said, I wanted to take this opportunity to tell you guys a bit about what I was doing at ESA for the past 3 years. Of course, between other things, but this might be a topic that's a bit different than the usual that we have over here, since it's based mostly on radiation effects. Right. The first question that I always ask, or that I need to define, is what constitutes the space radiation environment, and especially because typically what you think about is astronomy, astrophysics, but in reality, maybe not for this public, but here it's not all photons, and in reality, this is the thing that we care the least about. The main sources are first of all cosmic rays. Then we have solar particles, and in here I will highlight, I guess, that I'm hiding, which are solar electrons, protons, and heavy ions. Then we also have Jovian electrons. I'm not really going to talk a lot about this, but Jupiter, it's the main source of electrons in the interplanetary medium while the sun is quiet, so it's also a very important source. Then we have the trapped particles around the Earth, and induced radiation, so we have quite a complex system to work with. And having said this, let's just give you a bit of history. For those who don't know, and maybe this is not for this public, this is already a bit known, but we discovered galactic cosmic rays a bit more than 100 years ago, and from there things rapidly moved. So we discovered solar energetic particles in 1942. Then 5 years later, we invented the transistor. We had the Van Allen belts discovered about 1 decade later. So right now we already have a very nice picture of everything. And 2 years later, we discovered synchrotron radiation on Jupiter. So all the main sources by then were already known, even though they were not well characterized. And in terms of radiation effects, just to show you how these things combine, in '64 we had the first NSRAG, so this is the main conference for radiation effects in space, and this was just less than 20 years after the transistor was invented. So quite a fast track that we had from discovering radiation in space, inventing the transistor, and then having to care about radiation effects. The radiation environment in space, it's very well, it's highly modulated by the solar cycle. Here I'm showing you the sunspot number over time. So we've been tracking this for a really long time, and you see that we have this kind of modulation that over periods of around 11 years, even though we know that there are other cycles. And just to give you an idea of how this affects, how can we see this on the sun, you see two images here, one from 2019, so during what we call a deep solar minimum, and then in 2024, last year, this was the, if I remember correctly, this was the sunspots that launched the event that created the aurora that we had last year, that were observed quite south. And if you look at another image of the sun, here you can see quite the difference between the two. So while in the first, where we had no sunspot numbers, it was very quiet, very, I wouldn't say homogeneous, but quite stable. And here, during that event, you can see all the action that's happening on the sun. So this is one of the main factors for that controls the space radiation environment. And when we have this when we have solar events, we can get solar energetic particles, and I hope I can show you the video. This is a combination of images from different spacecraft observatories, and you can see basically during this is corresponding to this May event. Oh, sorry, to show the video again because it's quite fast. So you can see all these explosions that here, and also something that is quite interesting. No, I wanted to catch it, but here I cannot. Let me see. So after you have these explosions, yes, here you can see the image from our camera. You have all these dots, and these are caused by the energetic particles. So this is already the first radiation effects that you will see in this presentation. The way that solar energetic particles are correlated with the solar cycle is, as you would imagine, so during periods of high activity, so when you have a lot of sunspots, then we have more events, they are more intense, and then when we go to when we have the solar minimums, then we have less events. And then we have galactic cosmic rays. I don't think I need to introduce them to this audience, since many people work on this at LIB. But the main interesting thing for us is first the relationship between the elements. I'm pretty sure that I'm not going to have the time to cover it, but especially iron and is quite an important element for radiation effects. And then the second thing, which I guess everyone knows more or less, is that the cosmic ray flux is modulated by solar activity. But in this case, it's anti-correlated. So when you have the solar maximum, the flux is at its minimum, and the opposite as well. And this is something that is quite important when we plan the missions, and you will see also from flight data that it's quite apparent. Finally, we have the Earth's magnetosphere. So as everyone knows, we have the dipolar magnetic field at the Earth, and this helps us protect from the space radiation environment. Sometimes it also makes it worse, but in general, it deflects particles, especially solar particles, which have lower rigidities than cosmic rays. But these particles, and not only from the sun, but also the secondary particles from cosmic rays, can get trapped and can be accelerated in what we call the Van Allen belts, or the radiation belts. These are split into two regions, the inner and the outer belt, the inner being mostly dominated by protons, and the outer belt by electrons. Here you can see more or less a comparison between two models. So the first is for protons, the AP8, and here for electrons. Of course, we have different energies, but it's just to show you how the fluxes compare, or how their distributions compare. Something that it's quite interesting here is that these models are actually pretty much worst case as far as we know, because these were developed after the Starfish project from the US, which detonated a nuclear bomb at high altitude and sourced a lot of particles to the radiation belts. Something that's always curious. Also, something that you will see in this presentation is what we call the South Atlantic anomaly. I don't know how much people know about this, but this is basically an effect that we get because of the difference between the Earth's rotational axis and the magnetic field, which makes the particles in the inner belt having more access to the Earth, and it's very how do you say? And you can see the highlight here, which is above South America. Of course, this has been evolving with time, since the magnetic field is also not constant and it's changing. So it's up for low Earth orbit missions. It's one of the main issues that we have. It's this South Atlantic anomaly. Everything combined gives you quite a lot of stuff to think about. So we have the Van Allen belts. These are typically the lower energy parts, but they are in a way quite stable, and they have a high flux when you compare them with cosmic rays. Then you have cosmic rays, which extends, of course, to much higher energies than any of the other sources. The thing is that they are relatively stable, but the flux is quite low in comparison. And then we have the solar energetic particles. These are not steady, so these are stochastic events, but they they are characterized by a very high flux when you compare it with the other sources. All right. Okay, this slide I meant to remove it because I guess most people here know about this, but in my presentation, what I'm going to focus about is what we call mission reliability. So making sure that missions withstand the radiation environment and we don't lose them to it, at least that they can operate for the entire planned duration of the mission. So, and what are these radiation effects? Usually we put them into three categories. The first one being TIDs, total ionizing loads. This is a cumulative radiation effect where you have charges accumulating in the interface, usually between, for example, in a transistor between the gates and the substrate. And this will cause a shift on the gate threshold, that so the voltage that you need to put there to switch it on and off. Then we have among other effects, of course. Then you have total non-ionizing dose. So this, as the name suggests, is not ionizing. So this actually produces defects on the structure of a component, and this can have many effects. Especially in optical devices, for example, for solar panels, it degrades their capability of generating power over time. And finally, and this is going to be the focus of my presentation because it's where I focus my work at. These are single event effects. We have a bunch of them depending on the component, on the technology, but the most traditional ones are upsets, transients. We have functional interrupts, which actually have their own categories. And then latch-ups. And as the name suggests, these are caused by a single particle, not by an accumulation of events. And this particle causes the event, which can be even destructive. So there are two main mechanisms for which this happen in terms of the interaction with matter, and this is important because it explains why. Not why, how we do the testing of the components, so how we qualify them. The first one is direct ionization, so the particle goes for matter, ionizes the medium, and the component collects this charge, and it's this collection that causes the event. And then we have here I call it direct and indirect ionization, but what we are interested in is really in the indirect ionization. So we have a nuclear recoil from a proton that interacts with silicon, for example, and it's the recoil nucleus that is going to cause the ionization that in the end causes the effect as well. This maybe it's the most boring slide here, but I think it's quite important because it shows it's the basis of the analysis that I was doing. So this basically that you see here, it's a dynamic RAM on the left and a static RAM on the right. And the main difference is how they store data. So in the case of a DRAM, what controls the data is a capacitor. So you fill that capacitor and then you get a 0 or a 1 depending on your convention. While for the SRAM, it's a latch between multiple transistors. So for the SRAM, for example, you don't need to put anything there. So as long as you latch it, then the data is the memory cell is very stable. For the DRAM, that's not the case. So you fill in the capacitor, but then the charge can still move away from the capacitor. So over time, you need to recharge it over and over again with all its problems, but also with a few advantages, for example, being faster and things like that. So having said this, what kind of effects can we get? So in normal, here I use the SDRAM as an example, but you can think about it partially for the SRAM. So for the SDRAM, usually the access to the memory cells is done through what we call a mode register. And if everything is operating normally, you select which address you want to read, and when you read it, the word should come out fine. For the SRAMs, this part is not included. In terms of the radiation effects, so first we have single bit upsets. These are I think quite obvious by their own name. So basically we start with 0, and for example we start with a 1 and then we get a 0 from a single particle interaction. This can also be multiple bit upsets, for example. Instead of one flip, we can have 2 if the memory cells are close enough. These effects can happen to both SRAMs and SDRAMs. And then you can also get a latch-up. So latch-up is a bit different in the sense that it creates a short circuit in the component, and this can really destroy the component. So usually we need to have a few mitigation techniques in order for this not to happen. And if we know that they're going to happen a lot, we don't fly components, basically. Okay. For the SDRAMs, we have a whole new category, which are the SEPs. These are quite interesting. So in this case, the single event effect, it's not in the actual memory cell. It's in the control system. And this what can happen from this, and we'll see the different cases of SEPs, is that it can create up to thousands of errors, and this can completely destroy what you're trying to do with the memory. It can corrupt. If you're storing data, it can corrupt. If you're using this data to control subsystems, then it can give the wrong message, for example. So depending on your application, it can also be quite destructive. And then we have something, I don't know if this is the best plot to show, but we call them stuck bits. And the idea being that this retention time, it's the time bit that your capacitor can hold a charge, for example. Let's imagine. But if you have radiation effects or some defects really from the manufacturing process, this retention time can shift, and it can be increased periodically or even in a stable way. And this will create your stuck bit in the sense that you put a charge there, but it decays so fast that once you read the memory again, then you don't find this charge. And this can be quite problematic because if you're using a part of the memory specifically for something, then you always get this error. So there's no way to avoid it. Okay, and you can think that all these errors, maybe we are giving too much concern to them, especially the SEUs. But if you look at this nice pie chart, of course, this is from '96, so things have progressed since then. But it's the one that is most commonly used. This part here are spacecraft anomalies from radiation effects. So you see that it's almost half of all anomalies that we have are from radiation effects. And then of these, 80% are due to simple upsets, not latch-ups, not solar panel degradation, upsets. So which can be single bit upsets. And of course, you can think about how can this really affect your spacecraft so much if it's only 1 bit error. And there's always this very nice example from the ground, not from space, where in a 2008 Belgian election, there was a candidate that lost 4,096 votes. And after they had a redundant system, so they were able to check, and they found this difference, which is quite curious because if you change a bit, then you get this value. So this has been attributed to a cosmic ray. This change, and it shows how even on the ground we can be susceptible to them, and more so in space. All right, so how do we mitigate this? We have a set of processes that we call radiation hardness assurance, and usually there are 2 parts that you begin with. The first one is defining the radiation environment and the radiation levels. Right here, and usually this comes from models that we have, the orbit of emission, and then we can derive from there the radiation environment, and we can calculate the radiation levels inside a spacecraft or inside an instrument, for example. Then the second part, and it's the one that I'm focusing here, it's to evaluate the component's response. So for that, we need to test. We need to see when does it fail. And then we combine this with the radiation levels, and we can kind of categorize the risks. We can categorize the part. We can we can compare it to radiation design margins, and ultimately do a risk assessment and understand if we reject the part or if we accept. So of course, if we are looking for parts in space, then of course those are the ones that we accepted. This testing. Basically, because we have this direct and indirect ionization for single event effects, and I'm going to focus on the direct ionization, we cannot really test with all the elements that we find in space. We cannot test with all the energies that we find there. So what usually we do, we convert everything to LET, so to linear energy transfer, and we test different points. You can see here a nice example. We fit it to a Weibull, and we say this is the the sensitivity of a component. Of course, the first part is not necessarily true, especially now that we are moving into more integrated components. So things are getting smaller and closer together. Then having different elements can also increase the width of a particle's ionization and cause multiple events instead of one, for example. Also, we assume that this LET is constant in what we call the sensitive volume, so the part of the component that is sensitive, which can also not be true depending on where you are in this LET and the particle energy. Of course, this is a problem because we have to test it on the ground. We have limited resources, limited beams, limited money, limited time. So usually what we do is that we use single particles. We test it in a unidirectional environment, so only one direction, and you'll see that this has a big effect. And also we use accelerated particle rates, which is also a big constraint that we have. Of course, when you compare it to the space environment, nothing fits, but we kind of make it work, especially when you think about it in terms of engineering, use worst case analysis all the time. So that's what we go with. Then there's the modeling part. And this, when I went to ESA, this was the part I was interested in. I had already learned a bit about the testing, even though I never did SE testing. But the modeling part is quite interesting because we have to combine first the two parts, protons, so indirect ionization and the heavy ion part. And this heavy ion part has a few things that are interesting. In particular, we have this model called the IRPP, so integral rectangular parallelepiped model. So we assume that it's a parallelepiped, the sensitive volume. And the way we do that, or the way we put that into our estimation, so this n should be the number of errors that we're going to get, for example, or the number of single event effects, is that we build a chord length distribution, so the length that the particles go within this element. Of course, we are already making a lot of assumptions. First, that the particle goes, linearly, that the component is a parallelepiped. So this already constrains a bit, but it has been quite successful. Besides this, we also have, actually, I should have started from that. The particle spectrum is just not simply what you get from the environment. You also have to take into account the shielding that we have on the spacecraft. And this is an information that usually it's not very easy to get, even if it's a very well documented mission, like the ones I'm going to talk to you about, mainly because usually it's hidden behind the industry secrets part. So this usually it's one of the main variables that we have. So or the three parameters that we have for the model. What is the shielding? And then for the chord length distribution, there's, I don't know if you can see it here, maybe I'm on the wrong side, but there's the sensitive volume thickness, and this is our main unknown. So we cannot really experimentally test this, or we don't know how to test this experimentally, and basically depending on how much you estimate for it, you get a completely different prediction. So mostly it has been done over time in terms empirically. So we send the missions to space, see in terms of technology, the error rate, and then you kind of try to adjust. But this is not very well defined, and it's something that has intrigued me quite a lot. Is how can we determine it? Yeah. So 2-3 parameters. Okay. So this is where my fellowship came in line. It's called the Continuous Feedback Radiation on Radiation Effects in Operation, so CONRAD. And basically the idea is that when you're developing a mission, first, you have your expert on radiation effects. They prepare the mission, they test the components, they select them, they shield it, they design mitigation techniques, and then they hand over to operations. And that's where the loop usually ends. So as soon as the mission is flying, if everything's okay, nobody cares. And there's no feedback from operations. And that's where the CONRAD went, is that I talked with operations even when things were going well, and I tried to find if what we were doing on the ground made sense or not. So if it was valid or we were just hidden behind margins. And the first mission, or the pioneer mission that we used for this was SWARM, for a few reasons. The first one is that it has 3 spacecrafts in low Earth orbit. So the fact that we have 3, it means already that we can compare the radiation effects that they are getting. And then it had already been launched in 2013. So we had 9 years of data back then, but it's still ongoing. So we are still collecting data on this. And 2 of the spacecraft have the same orbit, while 1 is a bit higher. So again, it's nice for comparison. The orbit time, it's just there for reference, and you'll see that it has an influence on the analysis. Is 90 minutes. Here you can see the orbits. So the orbits, it looks like the Indian flag actually. I had an Indian colleague that was always commenting on this. But you see that they basically were their orbits were decaying. This is because of drag, since even at 400 and something kilometers of altitude, you still get drag. We had a discussion just before this, just before the seminar about this. And after 2022, we had to increase their altitude again, so that they didn't burn in the atmosphere. Why is this here? Okay, maybe just to show words. So what, in terms of radiation environment, we don't have a monitor on the mission, so that kind of doesn't allow us to make a direct correlation, but it's a very well-known environment. And I already showed you this plot. We know that we have the South Atlantic anomaly, so this is something that we already expect. And then if you see this blue part here and on top, these are cosmic rays. So if you go north, you get the field lines coming to the planet, and the cosmic rays get more access to these altitudes, and that's where you can get effects from cosmic rays. Maybe I'll just jump through this, but it's just to show the main instrument that I focused on was the onboard computer. You see that most of these parts have redundancy, so you see this double thing, and because it's so complex, it has many components inside. So this kind of work, it's a bit like being just excavating and finding what is sensitive, what is not, and what kind of data exists. And what I found, first of all, were two SRAMs, and I focused on these SRAMs because there were many moving parts with it. So the documentation was not always there. Operations were not always happy to help. And at least for the SRAMs, we know they are quite stable. So we know that they are only really susceptible to single bit upsets. So so I focused first on this to kind of trying to show like I could go from data that was unprocessed and undocumented to really get meaningful information. Here you can just see one is, I'm not going to go into detail about them, but one is the PM RAM and the other one is the SGM RAM. They have different memories inside, so we already expect different rates of events. They also have this scrub rate. This is quite important. So the scrub rate is the frequency that you read the memory trying to find errors and to correct errors. And this is going to be important in a minute. Something that for the results that is also quite important is that if you look here, you have the LET data and the proton data. So when you see energy, usually it's just protons, and LET is all the heavy ions. And something that here it's important is that if you look at the SGM RAM for LET, you only see a line. And this is because I didn't have ground data. I only had the fit, and there are problems with this, and we think it comes from the fit. And here I show you. So if you look into swarm A, B, and C, the different units, we have the number of errors in flight. They are not a lot, because these are radiation rad hard parts. So you don't really get a lot. This is for almost 1 decade. So the number is quite low. But then when you compare with the estimations, exactly how we do it on the ground, you see that everything is more or less in line when you calculate for the solar minimum and for the solar max, except the SGM RAMs. And if you look at the SGM RAMs, when you see if you look just for the trapped protons, you see that it's more or less in line. But if you look at the total, so protons plus heavy ions, then you see a huge difference. And this, we really could not explain it outside of, we don't have the ground test data. So the fit might be just a very worst case or from a different component batch. So that data is really not valid. But for the rest, it looks fine. So especially for the PM RAM, where we did the testing in-house, the values are relatively good. So showing that this kind of analysis can be done as long as you're willing to dig through the data and through the documentation. Also, something that I think showed that this was quite nice. If you look at the top plots, these are the locations of the errors in Earth's orbit. And what you would expect from what I've showed you before would be the South Atlantic anomaly, right? And then the cosmic rays at high latitudes. But in fact, maybe here you can see a bit, but you see this huge line here at longitude around 130 degrees, which is not expected. And there you kind of can't see anything. And this is because of the scrubbing rate that I told you about, which for the first was 34 minutes or 38, and this 60. Maybe I can just check very quickly. So 34 and 68, exactly. And if you remember, the orbit of the spacecraft are 90 minutes. So it's the time that they take to sweep across an entire latitude. What this means is that even if you find an error, it might mean that the error occurred 30 minutes before, and at that time you were in a completely different location. So if you sweep around the likelihood or the locations where the errors could have been, then you find hotspots. Of course, you cannot really find this South Atlantic anomaly very well defined. But if you look at the PMRAM, we go from this to this, and this is exactly the longitude that we expect the South Atlantic anomaly to be. For the SEPs, it's a bit more complicated. Of course, you see the highlight here, but because we are talking about a scrubbing rate of 68 minutes in an orbit of 90, of course, it's very difficult to track down the location. Also, we don't really have a very large number of errors, so statistically, it's very difficult to convert to location. But the idea is that it really shows that it must be coming. Most of the errors must be coming from the South Atlantic anomaly. Oh, am I in time? Okay. Then after having showed that this analysis can be done to the SRAMs, again, that we know very well and are quite stable, then I moved on to the SDRAMs, and this was quite interesting first because this LP, the EVS, blah, 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 is flying in a lot of missions. And this is a component that has been flying not for that long. So I mean, 2013 for space timelines it's not that much. So we really didn't have that much data. We didn't know how our assumptions, our testing would compare with the flight data. But here, because it's part of the mass memory unit on the satellite, we really have a huge amount of components. I just want to say that there are a few things that are difficult to see or impossible to see because the way that the memories are assembled is that we have basically two mass memory units that are redundant between them, and each of them have this kind of configuration with three cubes with 8 SDRAMs. And the way it works is that one SDRAM on each cube is working together to make up a word. So when we have an error, we know the address, for example, but we don't know if it came from this one, from that one, or from that one. So that is the main issue that we have with this. And if you remember, the SDRAMs that they have different from the SRAMs are these kind of SEPs, so single event functional interrupts. And this can come in various shapes. This is a table from the Jet Propulsion Lab. They did an amazing work on testing this memory on the ground. And they split the kind of SEPs into 4 types: band, roll types, and region types. There is this guy we never found, for example, and this we found a couple of new things. So maybe I can show you in a way that's a bit easier to digest. Here you can see what I'm calling memory 14 bank 4. The bank you can ignore, but the memory means that we are combining 3 memories, not just one. So this is a combination of these memories. And you see the normal SDUs here. And then you see the row types there. They are quite evident. So there are rows of errors. And then we have the band type errors here in green. So we can actually distinguish them in space because they take place very far apart in time. So this is something that is quite useful when you compare it with ground testing. And what did I find with this? First of all, in this, when we split this, when we separate these region type SEPs, we find that they actually have a twin structure that is 1,024 columns apart, so very suspicious. And this was something that was not found on the ground. The main reason for this, and I'm going to show in the next slide again, or highlight it in the next slide, is that when you test it on the ground, the rates are quite high. So it's very difficult just based on time to split the effects. While here, you can have several days between this kind of effects. So this was found in every single region type. So showing that this is actually a feature of this effect that we didn't know about. And now, more interesting and maybe a bit more difficult to understand, if instead of having this 2D map, if we just look at the address, we see this band type SEPs here, and then you see that we before we don't have any errors in this region, this address region, and then we get an error that's coming systematically. And this is what I was talking about that we call a stack bit, but the thing is that these two things should be completely separated. So this should the SEPs should come from the circuit logic, and the stack bit should come from the actual memory cell. And the explanation that we found is that, I don't know how much you know about this, but when you manufacture a memory, not all of the memory is going to be used. So when the manufacturer is going to test the different blocks, and it's going to find bad blocks, and then it's going to program the memory not to look at those bad blocks. And what we think that is happening is that this band type SEP is changing the logic circuitry, and then it's pointing it to this bad block, and that's where the stack bit is. So it was always there. Perhaps you don't even call it a stack bit; it's just a bad bit. But when you power cycle the memory, so everything comes back to the initial state, then this goes away. So that's a very, very strong evidence for this mechanism. And after we found this, it has already been confirmed on the ground as well. So with lower flux, with testing at lower flux. So we think the main culprit for us not to finding these effects is just the flux, because we accelerate the test and it doesn't really give us time to catch these effects. Again, showing that we should really look for them in space. Okay. Moving to another mission, to Bepi Colombo. It's the last one I'm going to talk about if I don't have the time. This is the first European mission to Mercury, and it's LEAP is heavily involved. So we have a leadership role in the radiation monitor, and it's composed of two spacecraft. One is from JAXA and one is from ESA, and it was launched in 2018. So in the meantime, we already have a lot of data. And again, we have the radiation monitor there, so it is there to give us context for the radiation effects. So in this case, we don't really have to rely on models, which is particularly good since we don't have that much data in the inner solar system, so outside the Earth magnetosphere, to make nice models. And there you can really look direct into galactic cosmic rays and to solar energetic particles. Here I'm just showing what exactly can we do. So BERM doesn't really measure cosmic rays in the sense that it can characterize them, but these are the background of the instrument. So one of the things that you can see already here is that since the launch, and in blue you can see the daily counts for one of the beams. You see that is already heavy modulated when you are here in 2024. And if you look at the sunspot number in red, you see that it's going up as well. So it's this anti-correlation between the cosmic ray flux and the solar activity. In terms of solar energetic particles, usually for this kind of effects, we care about the high energy protons at least. And here you can see that there were not that many events, at least when my analysis ended in 2024. We only had this very big event in February 2022, and this is quite a famous event that has many papers about, not for the radiation effects, but in general. So what can we do with Bepi? So we have the onboard computer, and of course I didn't really go into detail, but if you look at the onboard computer from Swarm, it's almost exactly the same. So at least the parts are exactly the same. The way it works internally, it's a bit different. So we don't expect exactly the same things. So we don't really know the address of the errors. This is because we are much more limited in terms of bandwidth. So we cannot really be continuously sending this variable. And also we have something that we call the mode register reset. This is kind of reinstating this initial configuration for the memory. So this kind of SEPs are being corrected almost instantaneously. So we cannot also not really catch them unless you are right in the address where they are happening. Then we also have redundancy for the onboard computer. It doesn't have the mass memory unit, but has the same PM and the SGM RAMs. We also have memories on the star trackers, and also Baron has something that we call the SCU monitor that has been flying in several missions, but I don't think I will have the time to cover the other missions at least. Okay, so if you put all of them together, you see the errors over time. First, you can see that the red one is the SU monitor. This is clearly the most sensitive one. We already knew about that. But then something that is quite important is to see if the rates are uniform. So if there's not a large variability between the different systems. And the only one that we find it's a bit different than the others is SGM RAM, I think is the A from the OBC, but we don't really have a big explanation for that yet, at least. So we just think it's part-to-part variability. But in general, especially if you look at the most sensitive ones, you can already kind of see a modulation if you really look deeply. But I will show you that if you integrate over time, it becomes evident. In terms of events from solar energetic particles, there's really not that many. The only outlier that we see is during this February 2022 event where we have, I don't know, 7 extra errors. So nothing too special to analyze, even though if you plot their timing, so these stars against the flux of the higher energy channels, you can really correlate it, but statistically it's very insignificant for any kind of study. So having said this, I decided just to focus on the cosmic rays and then really employ the modeling part. And here it's just the same slide. And here the idea is trying to figure out what these two parameters are. And the fact that you have, usually we just do estimations for solar minimums and solar maximum, let's say. And that makes it very difficult to get these three parameters. But the idea was, if you look this over time, so with the modulation that is happening, then perhaps you can estimate a pair of these parameters that better fits the data. And that would be your shielding thickness and your sensitive volume thickness. And this is basically what you see here. It's just a chi-square test, just to try to find a convergence point. You see here very clearly to one of the sets of the memories. And these are just here because this is how we usually do the estimations. It's a very worst case in the sense that it considers less shielding and it considers a lower sensitive volume thickness, which usually means that we have a higher rate. So this was applied monthly to every single. So everything was integrated for each month and repeated for the different memories. And when you do the estimations already based on this best fit, you can see here this line. You can actually measure quite nicely the modulation. Of course, it's very nice showing this here, but if you look at also the number of counts per month, it's quite small. And this usually means that I have to put together the different memories of the same type. And usually these are not shielded in the same way. So if you take one away, especially this shielding part can change even a bit drastically. And then you basically move around this line here. Okay. How much am I at time? Sorry? Hi, the thinkings. Total way. Okay. So maybe I will go to my backup slides. So one of the purposes that I had for this modeling and that I was quite curious is to try to reverse engineer these radiation effects. In the sense that most missions don't have a radiation monitor. If you want to study solar energetic particle propagation or cosmic ray propagation, you need data in several points. And since we are limited in the number of missions, and if those missions don't even have a radiation monitor, it would be nice to have a way to exploit the radiation effects. On the top panel here, you can see the Rosetta mission. This was ESA's mission to comet, I don't know the comet. But it was a very long-term mission, and it actually had a radiation monitor. So when you look at these three different channels, and I highlight the 49 MeV, which usually it's the higher the energy, the better it correlates with the effect. You see that in the first event that occurred, you see a small increase in the EDAC in black, but not that much. But then when you have this huge spike, which went to much higher fluxes, then you actually see the number of errors increasing quite a lot. Even though this is not in flex units, so it's still in counts, and we have a problem in getting back this data because the documentation, especially after the mission ends, it's very difficult to get. But it already shows that since we have a very big correlation, if we can characterize it, maybe we can actually use it as a monitor. Same for the Mars Express. This EDAC, it's an error counter on the mission. And you see that we have this RAD though. So RAD is it's actually a radiation monitor, but on the ground of the planet. And if you look at the dose called by protons above 106 MeV, you actually see that they also correlate quite nicely. Again, this, of course, we expected this, but it's good to have this strong evidence that both correlate. And the guys at NASA went even further. So for the Juno mission, this is NASA's mission to Jupiter, which I think it's still active, or no? Yeah, it's still active. But this mission doesn't have a radiation monitor. Actually, this is a trend on NASA missions that now they don't fly radiation monitors. And so what they did is that they picked up their cameras from the star trackers and even from different instruments, and they went to look into the background on these cameras. And but they actually had spares of the instruments, so they went to the lab and they tested with heavy ions, with electrons, and with protons, and they basically made a relationship between the intensity of the background of each cell. So here you can see a huge one, which they identified as an ion, and then a smaller one as electrons. This goes really deep, and they can actually identify a set of elements based on this. But I just wanted to show this nice plot. This is from a paper that I reviewed, and that's why this is here, because it was I requested it. And you see that the stars are the ions that they identified during their passages through Jupiter. And you see here the Jovian radii, the magnetic shell. And in blue and in green, these are data from the heavy ion detector on the Galileo probe, so an older mission to Jupiter. And you see that when you have this higher count rate, not flux, from helium, and here it was so carbon and sulfur, that's where you actually have these errors. When you go deeper into the system, and here you are outside the part where you have these elements, then you don't see as much counts. So it already shows that they actually can find a region where you have more heavy ions than others, just based on using the background from a camera. So again, very strong evidence for this. In a few conversations while I was at ESA, I got to know that they have the same camera on Swarm. So now they are developing a data product that can reconstruct the proton flux based on this. So which is quite nice, since it was not done for that purpose. Okay, so I can go to my take-home message, and then maybe I will just show a backup slide that I find interesting. Is that okay? The radiation is one of the main showstoppers for space missions. Of course, that doesn't stop us from going, but we need to put a lot of work into them to be able to have them operating. And then that's maybe we didn't really dig a lot into this, but it's I think it's always a very important message, is that the key is risk mitigation, not avoidance. So you cannot really avoid. So if you see on the news that the mission had an anomaly and stopped operating, this is because we really cannot protect against everything, which we can just decrease the risk and find a sweet spot between the cost and the likelihood that it's going to succeed. Then it's that this is a data-driven world, even though the data is not a lot, but it's very empirical. So we are talking about the engineering realm, and it was where I had my most interesting discussions, was coming from LIP, where you're trying to narrow down the error bar. While for engineers, if it was within a factor of 10, it was fine because it was going to survive. So that led to very interesting and discussions. And then I think this is also important, especially for the future, where the number of radiation monitors doesn't seem to be going up, but down. Is that everything, and I put this in quotations, is a particle detector if you calibrate it well enough. Of course, the data product that you get might not be the best, but you still get some information out of it. Okay, and yeah, that was it.